Okay, so in this video we're going to start talking about aircraft instrumentation. Now, aircraft instruments are something that you're going to have to deal with a lot. This is the primary point of interaction for the pilot, and so therefore it becomes like one of the primary canaries in the coal mine for a lot of maintenance issues. You'll see people say like, hey look, this it doesn't seem like that these two gauges are syncing up like they should, or this thing is lagging, or we're having some sort of indication in the cockpit of X, Y, or Z. This is especially true the more complicated the aircraft becomes. So when you start looking at a 737 versus a Piper Aztec, you're going to see a horrendous shift in instrumentation and complexity of the systems. And every single system that gets piped in, you're getting a whole new suite of circuit breakers, and you're getting a whole new like indicating system, and usually more annunciator lights. And so whenever you sit in a cockpit of a heavy commercial airplane, you start seeing that there's a lot going on the plane itself. There's it'll even have redundant systems that all have their own indicators and things like that. So let's start trying to, anytime that you have anything in life that's really, really complicated, one of the easiest things to do, or the best ways to kind of proceed with it, but maybe not to understand it, and we can get into systems thinking. Ask me on the hangar floor, and I can kind of break this down to you. But like for our purposes today, breaking it down into its smaller component or analyzing it is usually the quickest way to start to gain a really good understanding. So let's break down our instruments into three families. Family number one are going to be engine indicating instruments. These are things like your RPM gauge, your exhaust gas temperature, your suction gauge, your amp meter. These are things that what it's telling us, what is the airplane doing? Like what's going on under the hood out there? Is the engine running correctly? Is it producing the suction that we need it to produce? Is it producing the amount of RPMs that needs to be produced? Is it, what's happening? Now, as you kind of grow and as a mechanic, you'll start to see that, hey look, this the mag drop on this plane is a little bit low, or a little bit too much. But like I'm also seeing this other indication over there, and that kind of helps me kind of like triangulate what could potentially be happening. Maybe that there's some sort of electrical failure. Maybe the points on the mag's off, or who knows what the problem is. The point being is that the engine will tell on itself if you listen to it, and the way we listen to it is by paying attention to the engine instrumentation that we get in the cockpit. Now, the next category of instruments that we get are going to be navigation instruments. These are instruments like the compass, or the ADF, or the VOR, or any number of things. Nowadays, a lot of times your navigation instrument is going to be just a panel, like in the Lear, it's a Garmin 430. It's just a flat panel that just tells you where you're at, what altitude and speed you're going, and that also gets hooked into a system called ADS-B, which basically transmits that information out to the wide world, so that way everyone else can know what we're doing. And we'll get into that whenever we get into talking about communications and all the complexities that lie in that. But essentially, this category of instruments basically just tell us where we are. And so since it tells us where we are, we can either then tell everyone else where we're at, or it will tell everyone else where we're at. But either way, you have engine instrumentation that tells us what the engine is doing, and like what's happening here. Navigation instrumentation tells us where we are and tells everybody else where we are. And finally, the last category is flight instrumentation. That tells us what the plane is doing. So these are instruments like our artificial horizon here, or our VSI, our vertical speed indicator, and that tells us, hey look, the airplane is in this flight configuration. This this wing is up, that wing is down, we're pitched up, we're pitched down, and it's absolutely crucial for you to, as a pilot, to understand exactly what those mean, and then how to react based on the indication that's coming in there. It's also heavily reliant from a maintainer standpoint on the air data system. And so like if there's something wrong with the air data system, and even if it's just in one place, in one line, it might affect multiple of those systems. And you start to kind of build a troubleshooting kind of diagram in your brain that like, hey, look, if I see that the altimeter is stuck and doesn't want to come down, it could either be A, that altimeter just like died, or B, there's something that's stuck inside like inside the static line. And then if it's stuck inside the static line, then I also know that the VSI should be off as well, and I can look there and see like what's going on with all these instruments. Or if you have a squawk, the pilot comes in and says, hey, look, I have these things, with like, oh, air data, and then like you can start to look for trends across all of those different systems to know that, hey, look, this system, because I know how it works, if this one thing happens, it'll affect all these other things. And so we know that based on knowing the flight instrumentation really well. So those are the three kind of categories of instrumentation that you're going to get inside of a cockpit. Now, just like anything else in life, instruments have their limitations and ideal conditions to which they can operate in, and conditions that they can't operate in. Every single one of these systems is a little bit different, but ultimately, what you're relying on is the system to measure the outside world and then feed data into the cockpit. Now, if there's something going on in the outside world, let's say like there's icing that's out there that could potentially like clog a static port or a pitot tube or something like that, then we need to take that into account whenever we get instrumentation failure or some sort of like wacky reading that we know is not right. There's also other things that can affect things. So like if you turn on the radio, it's going to have an effect on the compass because you're emitting that electromagnetic interference into the area that the compass has to operate in. So we have to take that into account. All of these instrumentations, they're just a proxy for reality. They're not necessarily like this is what reality is. And because of mechanical inefficiencies, because of outside dynamics, because of miscalibration, because of pilot dynamics, or maybe not being maintained very well, then these instruments have their limitations and have their potential fallacies that could happen as well. Now, we as maintainers are going to try to limit that as much as humanly possible, and the pilots are going to try to fly the airplane and operate the airplane in a way that doesn't expose the airplane to like undue complications. However, life happens, and so that's something that we need to take into account whenever we are working and troubleshooting an aircraft. Sometimes things just break. It's just as simple as that. And like there's not necessarily a really easily found cause on why it broke. It could have been a manufacturing issue way back when, or some sort of like problem with the way that the rock formed that eventually was refined into steel that was placed into the instrument, and it finally just gave away. All of these things are things that we need to take into account whenever we are dealing with instruments, that we know that, hey, look, that the best way to mitigate a lot of that is have multiple points of data on one system. So if you have like a high engine oil pressure, then you need to figure out like, okay, is that engine oil pressure really high, or do we have a transducer that's bad, or is there something else? And the way that we do that is we put another transducer in there and then compare and contrast. If we know that this transducer is good, and then we put that in there, and we still see the same indication, that at least means that the system itself is what's causing it, not necessarily the transducer. Just like we were troubleshooting yesterday with the light, it's very, very similar in that you want to swap out components and try to see if the issue follows, and then from there go on about trying to understand what information is being produced inside of the airplane that's being fed to that point of data collection that's causing it to be all weird or produce the effect that's happening. Now, another thing to take into account with instruments is range markings. Range markings are going to tell us, hey, look, this is what the instrument can measure, and this is what the different markings mean, and a lot of times they're going to be color coded. One of the easiest places to see range markings is on an airspeed indicator. On an airspeed indicator, you'll have a dial, that will have a circular set of numbers that indicates how many knots indicated of airspeed that's hitting the airplane. Now that starts breaking down into some interesting points, because it's not just like how fast the plane is going, it's rather how fast the relative wind is going over the top of the airplane. So that means that if there's a headwind, then you have a higher knots indicated, even though your ground track, how fast the plane is going across the ground, maybe only say like 60 miles an hour, but you might have 100 knots indicated in the cockpit because of a 40-mile-an-hour headwind. So there's things to keep in mind. But that's what those numbers indicate, is what's the speed of the air going over the top of the wing. All right. Now on that indicator, there is a white arc. That white arc will tell you when you can operate the flaps. Now, flaps have a range, just like anything else, that if the plane is going too fast, you could cause structural damage to the flaps of the airplane, or whatever. It's also on this in particular airplane, the flaps is cut off at, it looks like 70 knots. So at 70 knots, you don't want to operate flaps below that, likely because the stall speed is probably right about there, and the airplane just simply won't fly beyond any slower than that. Now the green arc is the arc where it's fine to operate the airplane. It's like the airplane is perfectly fine operating from 75 knots all the way up to 225 knots. It's a great range that you can adjust your power settings and optimize based on how far you're going, how fast you need to get there, how much fuel you have, how much fuel you choose to burn. Now beyond that, you'll end up having a yellow arc. Now that yellow arc will tell you, hey, look, this is kind of dangerous, because you're going so fast that if you hit like a bump and turbulence or something, that you could damage the airplane. And so you want to be cautious there. You generally don't want to live in the yellow arc. If you can pull it back and be inside the green arc, then you know that you're mathematically sound to operate the airplane beyond that. Now there's a red line at right about 250 knots, and that means that that's the VNE, or V speeds will always be V is equal to speed, just like in physics, and NE is never exceed. Don't go faster than this, because the plane's not rated to fly that fast. So if you get into a dive and you nose over, there's nothing saying that like the wings won't like come off, because there's so much pressure on them due to that indicated airspeed. The plane will literally just fly apart. Now every single aircraft or instrument has an arc of some variety, or it has some sort of marking on there that'll tell you that just about that. Green is generally always good, and red is generally always bad, and yellow is kind of like in the middle. So if you look at our tachometer tells us the same thing, that like here are the green operating ranges for the engine RPMs, and here's like where the engine is going just a little bit too fast. Like we need to not exceed that, and this is going to come at about 2,600 RPMs right there. Other markings that are not necessarily indicated are good or bad is like our artificial horizon. It will tell us basically what degree the airplane's wing is pitched up, or where the nose is at. The wings on the little airplane in the middle of the artificial horizon will indicate the right and left wing. The dot on the horizon will indicate where the nose is pitched up, and then the lines that are on the backdrop and then around the edges of it correspond to different degrees of flight attitude, be it if it's pitched over one way or pitched over the other way, so on and so forth. Now every single one will basically be dictated inside of the maintenance manual that says like, hey, look, this is what all this stuff means. It's also in the flight manual, because pilots also have to know this. And so like if you ever get a question where like, well, what is that? Is that good or bad, or what does that mean? A lot of times you can just go to the flight manual, or the POH, with the pilot's operating handbook, and get that information right there if it's not in the maintenance manual. Either way, just know that those markings are not just there for fun. They all mean things, and they all mean things for us as maintainers. Let's start our breakdown of the different instrumentation systems. So we've grouped them into families. We have flight, navigation, and engine. We're going to start with navigation, with two of the most iconic and age-old navigation systems that are out there. One is the thermometer, and the other one is the compass. Now, whenever aircraft first started flying, they basically had nothing. It was an engine with maybe a fuel gauge to let you know how much fuel was left, and flight controls and some wings that are made out of wood and canvas, and that was it. But as things progressed on, people realized, hey, look, we need to have, we need to understand where we're going, and so they start throwing compasses in there. Now, compasses get really complicated, and we'll talk about those in a minute. But we're going to talk about the simpler one, that is temperature. Now, you might think, well, why is temperature a navigation aid? Well, temperature affects a lot. It will impact the density altitude of the air that the engine is taking in. That's changing the amount of fuel that we can put inside of that fueled air mixture, which then affects our performance. And so they realized this early on, that the rapid changes in altitude had direct impacts on how the engine performed. So therefore, they put a free air temperature, or a FAT gauge, or a outside air temperature, an OAT gauge. Both basically is an outside thermometer, and depending on the manufacturer, like they'll call them one of those two. They put those in the airplane so that way they can read what the temperature was on the outside very early on, probably predating the compass. So let's look at what the 8083 has to say about temperature measuring instruments. Now, temperature measuring instruments can come in a variety of forms. They look a little bit different on every single airplane that you get. Like on the Aztec and the Cherokee, they're both the inside the windshield. You screw a hole through the windshield. You stick a probe through there. You put a shield or a sheath on the probe, and tighten them up, and it just sits inside the windshield like that way. On the Lear, it's totally different. They're going to measure it from different instrumentation systems and give you a digital display inside of the cockpit. So, but every aircraft is going to be slightly different. But either way, the outside air temperature has a lot to say about the way that aircraft performs, both with its engines, and then we'll get into de-icing and like the implications for flight controls later on. So let's talk about non-electric temperature indicators and how they work. The 8083 says the physical characteristics of most materials change when exposed to changes in temperature. The changes are consistent, which is the expansion or contraction of solids, liquids, and gases. The coefficient of expansion is different from most materials and varies and is unique to each material. Most everyone is familiar with the liquid mercury thermometer. I'm sure that you've probably seen that as the temperature changes, the thermometer comes up, especially if you're a little kid. Your mom puts the thermometer underneath your tongue, at least the old school mercury ones. As the mercury is exposed to heat, it will raise up, and it does it very consistently, so we can grade the the amount of mercury that's in there. We know that, hey, look, if it is at 100 degrees, it'll expand so much, and so we put a mark on the little glass tube that it's in, and then that we know about where your temperature is, no matter what. Both the Aztec and the Cherokee both have what's called a bimetallic thermometer in there inside the window. So let's see how a bimetallic thermometer works. The bimetallic thermometer is very useful in aviation. The temperature sensing element of bimetallic thermometers are made of two dissimilar metal strips bonded together. Each metal expands and contracts at a different rate when temperature changes. One end of the bimetallic strip is fixed, the other is coiled. A pointer is attached to the coiled end, which is set in the instrument housing. When the bimetallic strip is heated, the two metals expand, and since their expansion rates differ, they are attracted to each other, and the effect is that the coiled end tries to uncoil as one metal expands faster than the other. Essentially, you have two metal strips in there, and as the temperature changes, the expansion and contraction, of those metals also change. Now, as they physically move, because of that change, it moves the needle one way or the other. And since we can mathematically work out exactly those rates of expansion, then we can then say, hey, look, at 100 degrees, they should be in this configuration. So we put a little pointer on it, and we say that's 100 degrees. We say, hey, look, at 50 degrees, they should be at this configuration. And then we put another tick mark, and then we can just extrapolate from 2 points all of the other gradations of temperature that's on there. And so that there you have a non-electronic, just simply reacting to the physical environment instrument that says, like, hey, look, this is what the temperature is inside outside. Now from that, you can turn around and say, hey, look, this is what the temperature is. This is what our fuel consumption should be. This is what what the oil should be doing. This is something we should be worried about. We should be worried about ice. We should not be worried about ice. So on and so forth. Very, very important flight instrument that often gets overlooked because it's so simple. I mean, it's just two strips of metal tied together. Okay, so another temperature gauge that you'll see a lot is actually not tied to navigation. It's tied to the engines. Specifically, engine oil temperature is like probably the easiest one to kind of point out. But there's also, like on helicopters, you'll have transmission oil temperature that's a part of it. The tail rotor gearbox oil temperature, and all of these have electronic indications inside the cockpit. Just like you would have EGT and TGT on the Lear. The exhaust gas temperature coming out of the exhaust will tell you how hot that engine's running, and it's in there. Now, you cannot use a bimetallic thermometer for that, simply because like it's a long ways back there. Like if you think of a tail rotor gearbox on a helicopter, it's good 30 feet behind you. Like you can't really physically make that work with a simple bimetallic thermometer. So you're going to have to come up with a different way to do business. And so luckily we've come up with one. Now, as temperature changes, metals expand. If you can remember back in our physics, that metal expansion is basically like you have two atoms that are set right there. And as they get hot, they get more energy. As they get more energy, they need more room to move. And so they start pushing against each other, and they get bigger and bigger and bigger. And that's what causes the metal expansion to happen. Well, come to find out, we can also mathematically know an element or an alloy will expand at a certain coefficient. So we know that for every 1 degree of temperature increase, we get 1 degree of expansion. As we get that expansion, we also know that we have a different rates of electric conductivity, because those atoms are further and further apart. It becomes harder and harder for the electrons to jump, and so we have different rates of resistance inside of a circuit based on the temperature. So as these things start to increase, then that gives us a different electrical configuration inside of a circuit that we can then translate into temperature. We know that, hey, look, whenever it's reading 1 ohm, it's 10 degrees. But whenever it's reading 2 ohms, well, it's 5 degrees, or whatever the mathematical relation is to it. That forms the basis of how electrical temperature sensing is built. And so what you'll end up having is a probe that will go into an oil bath of some variety, or into a gas flow like on an EGT, and then it'll simply just run an electrical line back to a sensing unit, and that sensing unit, all it basically does is says like, hey, look, I'm putting 1 volt in there, and I'm seeing this kind of reading on the electrical side, so therefore the temperature must be this, and then that's all it's really doing, and that's what it's displaying inside the cockpit. And so these are really, really common. But because they're a lot more complicated, and they're not so locked in physically like our bimetallic thermometer, well, you can have a lot of errors with it as well. And so you'll end up doing a lot of resistance checks on things like that to know, is there an internal resistance that has crept up because of degradation over time. They're also in really hostile environments where things are heating up and they're condensing. And then that's causing a lot of stress on the metal, so you could have erroneous indications because of that. There's all these factors you need to take into consideration with those systems that could cause temperature to read artificially high, artificially low, or what have you. But know that that's the way that most of your temperature indicating systems are going to operate, is through an electronic means that way. Thermocouples are by far probably the most common temperature sensing construct that you'll find anywhere on the airplane. You're going to see them on the engines. You're going to see them on the airframe. You're going to see them everywhere. So just know, you can always think that thermocouple is just synonymous with just temperature sensing. That's what it is. Yes. The thermocouples are cool in that they use the wires' internal physics to limit or create a flow of current. So essentially, as the wire heats up, you'll get a temperature indication. This is really common with fire suppression systems, where they where like you won't get a light unless there's a certain temperature that gets reached. Once the certain temperature gets reached, current can flow, then you get a fire warning light. But this can also be used for any number of other things, because as the wire continues to heat up, more and more current can flow, and there's a mathematical relationship between the temperature and the amount of current that can come to the cockpit, and that just gets translated into a digital signal. So they're really cool, really useful to be used. As we get into engine instrumentation specifically, and fire suppression systems and things like that, we're going to talk a lot more about these temperature indicating systems, because they become central to knowing when to pull a fire handle and when not, and as well as how engine systems respond to different changing conditions. So just keep your thinking hat on to understand you have like thermocouples, you have ratio meters, and then you have the bimetal metallic thermometers that are out there that you need to know. Another specialty air temperature system is going to be a TAT, or a total air temperature measurement. What that will do is it tells the airplane, hey, look, this is what the air temperature is outside, but then it takes into account the speed of the airplane, because the speed will, as it goes through the air, will change the temperature reading, because it's either going to get really cold or really hot depending on what speed it's at. So that has to be taken into account, and a TAT gauge will do that. Now, we don't have any here on our airplanes because they simply just don't go fast enough to really to warrant that. But you will see those 100% on heavy commercial airplanes that are flying, close to the speed of sound on a regular basis at 40,000 feet. And so, just know that that's what a TAT does, or TAT gauge does. You'll usually almost always see them on the sides of the airplane, close to the cockpit, in and around the angle of attack sensor and the static ports. The bimetallic thermometer, or the board-on tube approach is convenient, but it's antiquated, and it can't be integrated very well, if at all, into most systems. You're almost always going to be reduced to some sort of electronic means to detect temperature. And that temperature could affect your ECAS system, your engine controls, your FADEC, or whatever. And so, if you have one of these sensors going out or reading incorrectly or whatever, the second and third order effects of that could be pretty drastic, and it could also lead you in a bizarre way. Like you're looking, you're saying, well, why is the fuel running low? We must have a fuel flow problem. It's not. What's happening is that the FADEC is seeing that the temperature is going up, and they're trying to optimize for that temperature, and that's causing your fuel flow to be pulled back, and so you're not getting the power assurance that you thought you were. And it all comes down to, it was misreading the temperature. But you'll go off on this crazy tangent that's down there. That gives us a chance to talk about the fault isolation manual and your systems manuals, so that way, whenever you have an indicator, consider all possibilities. Look at your FIM, look at your systems flows, look at all these different things, and think what are all of the possible variants of this problem that we're starting to see the symptoms of. And then from there, start trying to find ways that you can quickly and efficiently eliminate it by double checking different things, or finding different indications of the cockpit, and then start to whittle down to what this has to be it. It's the old Sir Arthur Conan Doyle thing, that if you eliminate the improbable and whatever remains, or eliminate the impossible, whatever remains, however improbable, has to be the truth. That is troubleshooting in a nutshell, and that will absolutely come into impact your temperature sensing gauge troubleshooting. Okay, so let's talk about compasses. Now, the compass was one of the first navigational instruments ever to be put into an airplane. And rightly so. You think about whenever the airplanes first started flying, and they first started going over long distances. At first, all they had was they would just kind of follow rivers, follow roads, follow things, do things that they call pilotage, where you just simply fly along and you kind of guess where you're at based on what's below you. Now, obviously, there's some problems with that. Like if you're trying to go somewhere, say like across the Atlantic, where there is nothing to follow, it's just water for miles, that's a problem. The other problem is like what happens if all of a sudden like the weather degrades and next thing you know you're in the clouds, or there's fog, or it's at nighttime and you can't see things, especially during the early part of the last century where electricity wasn't just so rampant. Things were just lit up for miles and miles and miles and miles. So they needed a way to get to navigating. Well, at the time, the only technology for navigation that existed was either trying to calculate with a sextant where you're at on the globe, which won't work for an airplane because it moves too fast, or a compass. So obviously the compass won pretty quickly. And they started to try to figure out, okay, like if I'm going to fly from point A to point B, I need to fly due east. When they took off and they just followed the compass and followed it east. But then they started discovering really quickly that there's a lot of challenges with that. Either the compass is totally reliable, and that's one of its best things, is that like being that it works the way that it works, it like you don't have to worry about it, being off per se, but there still are, it's susceptible to a lot of different challenges that can throw that indication off. But let's start with just trying to understand how the compass works. So, and we don't fully understand why this is yet, even in this day and age. But the Earth has an electromagnetic field. A lot of people believe it's because of the way that the Earth's core moves. It produces an electromagnetic field that is just like any other magnet. It has a north end and it has a south end. And because of that, and because of the reliability of that, we can take another magnet, suspend it in some way, be it in a liquid or off a string or whatever, and it will align itself, the smaller magnet, to the Earth's magnetic field, and always point, one end will always go to north. The north end of the magnet will always go to the north end of the the south end of the magnet will always go to the north end of the Earth's magnetic field. And so since those attract, we can then start to have a certain amount of reliability on which way the compass is pointing at any one point in time. And so we know that the compass is pointing north, then we just need to go to on a right hand angle to go east, or make a left hand 90-degree angle to go west, or go the exact opposite way to head south. And for centuries, man has navigated using that very, very principle. Now, once it got placed into the airplane and you started going much faster than, say, a ship, then you started running into all kinds of interesting challenges with the compass. So let's look at some of those challenges, and we're just going to go through the 8083 and all of the things that it says about compasses, and then we're just going to talk about it as we go. So 14 CFR Part 91, Section 91.205 requires that aircraft with standard category airworthiness certificates have a magnetic direction indicator for VFR flight during the day, meaning everybody has to have a compass of some variety. Now, we're going to find out really quickly that there's a bunch of different types of compasses you can have. Some of them are more susceptible to problems, and some of them are less susceptible to problems. Some of them are totally foolproof, and they work every time. So it just depends on what kind of compass you have. So an ordinary permanent magnet that is free to do so aligns itself with the direction of the Earth's magnetic field. And upon this principle, an instrument is constructed that the pilot can reference in for directional orientation. Permanent magnets are attached under a float that is mounted on a pivot, so it is free to rotate in the horizontal plane. Now, this is on a float. Now, it says that. However, there are multiple different ways to actually accomplish the same thing. We're going to get into it here in just a second. But just know that in order for a compass to work, it has to have a permanent magnet. It can't be an electrical magnet. It has to be permanent. And it has to be free-ranging, so that way it can spin however it needs to spin to align with the magnetic field. All right. There are accuracy issues associated with using a magnetic compass, like we've said. The main magnets of a compass align not only with the Earth's magnetic field, they actually align with the composite field made up of all the magnetic influences around them, meaning local electromagnetic influence from metallic structures near the compass and operation of the aircraft's electrical system. This is called deviation. There's a couple of words that we're going to want to like really kind of focus on. Deviation is one of them. A compass will deviate whenever it is near metal. So like if it's near another ferrous metal, it'll want to attract to it. So if you remember the old Anthony Hopkins and Alec Baldwin movie, The Edge, where they get lost in the Alaskan wilderness, the thing that threw them off is Anthony Hopkins' belt buckle. He would stand too close to the little paper clip that they made into a magnet, and it would spin around and spin to his belt buckle. So they are always heading the wrong direction. And so they would head one direction, and then they would take another reading, and but it was always like telling Anthony Hopkins, or they were always pointing the direction of Anthony Hopkins' belt buckle. And for about 15 minutes of the movie, they wander around, and it's this big drama fest, and then they realize, oh, it's because his belt buckle threw the whole thing off. That is a serious concern inside of airplanes. Now, we generally don't have to worry about it being attracted to ferrous metals. However, anytime that we have anything that's electric on, it emits an electric magnetic field, and that will cause the compass to turn. Matter of fact, if you want to experiment with it, you can crank up an airplane, watch the compass, and then key the mic. And a lot of times you'll see the compass jump because it's all of a sudden like it's keying that electromagnetic field, and the compass will jerk because of that. Now, there's a lot of things that get done to try to prevent some of that, like grounding the radios appropriately will help curtail a lot of that. And then isolating the compass away from things that will cause deviation is another step in the right direction to try to make sure that it's taken care of. You could also adjust the compass, like whenever we start talking about compass swings here in a minute. There's adjustments that can be made to help combat some of that deviation, and then ultimately it will come down to the compass card, which basically says that, hey, look, with the radios on and with these different configurations, then the compass, whenever it's pointed at 180, will actually read 175. So you always want to take deviation into account of, like, whenever you're doing navigation, you want to sit there, plot it all out, and say, like, oh, look, I need to add 5 degrees because my compass card is off. But that's deviation. That's something that you as a mechanic will have to become intimately familiar with, because compass swings, the process for calculating that deviation is something that you'll do on a regular basis. All right, so a compass swing should show a deviation, should never be more than 10%. So that means that if the compass is showing more than a 10% deviation, it can't go on the card. Something has to get fixed. There's something that's not right there. Another compass error is called magnetic variation. This one's pretty cool. It's caused by the difference in the location between the Earth's magnetic poles and the geographic poles. Now, this is an interesting one. Let's say this is the Earth, and the magnetic pole is sitting up like so, right? Now, the geographic pole, north will always be north and south will always be south. And there's mathematical certainty of that's where those two things are. And they're just references for us, for just human beings, say, like, that's what we're going to call north, that's what we're going to call south. However, over time, the magnetic pole wants to flip. And as it starts to flip, this is what happens. You'll go through a period of time where it's very, very synced up with the geographic north. But then over time, it starts to deviate, and it starts to kind of go a little bit over, a little bit over, a little bit over, a little bit over, to where now, if you go up to the North Pole, and you stay on geographic North Pole, the actual magnetic North Pole is like way over there. Same thing with the South Pole, and that's because it's starting to flip. And so, like, you'll go, and then it'll go through a period of time where it's just like, it's all wacky, and it's just all off. And then all of a sudden, it'll pop back up and it'll be lined back up. That creates havoc for anyone that's trying to navigate, because, as you can imagine, if you're going over a long distance, and that 2 or 3 degree difference in variation doesn't seem like any big deal. If I'm just going to go across town, it's like, well, it's only 2 or 3 degrees. Even if I follow this track, I'll go off a little bit, but I can see where I want to go, so I'm just going to make a correction. But when you're talking about over 2,000 or 3,000 miles, you're going across the United States or something like that, then you could be shooting for New York and end up in Ottawa, and so yeah, that has to be something we have to calculate for. So us as maintainers generally don't ever really have to mess with it a whole lot unless you're doing something with some sort of advanced avionics where they're having to take that into account. But most of the time, the performance data and the programming has already done that for you. Where it really starts to manifest is whenever you're doing like VFR. Cross-country flights using a magnetic compass as your primary navigation tool. That you're always flying like 1/8. Well, the problem with it is that like it may be geographically 1/8 from your position, but you're not taking into those what they call isogonic lines and adding in the variance that you need, or taking away the variance. So depending on where you're at and where you could either have to remove degrees from your heading that you're going to fly, or you're add to it. There's an old saying that east is least and west is best. It means that if you're on a western isogonic line, you add it. If you're on an eastern isogonic line, you have to take it away. Now, you guys that have been in the military are probably very familiar with this, because land nav, you do the same thing. You'll look on your map, and you'll turn around and say, hey, look, like we want to go from point A to point B, but we have to add and do all of this math, and it's on the bottom of every single military map to help you, so that way you don't get confused or lost. But that's variation. Okay, another one that's interesting. Operation an aircraft near the magnetic poles is also what's known as dip error. Dip errors manifest themselves in two ways. The first is called acceleration error. If an aircraft is flying on an east to west path and simply accelerates, the inertia of the float mechanism causes the compass to swing to the north. So if you're flying around, you're going like due east, and you just firewall it and just want to take off, all of a sudden the compass is going to tell you you're turning. But you're looking out and you're like, I'm not turning, like I'm just going straight. Well, the reason being is because that compass, all of a sudden, like you have physics that's involved, and it's sitting there just floating around and can spin freely. Well, as you start to accelerate, that inertia will turn and spin that compass, and it'll show that, hey, look, I'm going. It'll make it seem like you're going north, and then it'll settle, it'll level out, and then spin back around back on your regular heading once the energy is kind of like dissipated from the turn. Okay, rapid deceleration will cause the swing southward. So if you're doing the same thing and you decelerate with flaps in, whatever else, the compass will spin all the way back around, make you think that you're turning again, which you're not. So this is something you have to keep in mind, especially when you're like instrument flying. You're not looking out. You're not verifying all these other types of things with your compass heading. If you're only paying attention to your compass heading, this could really throw you off if you're not cognizant of it. So these are those are turning errors that happen. But we generally, as maintainers, we're never going to have to really mess with that. Just know that could happen. So if all of a sudden you get a write-up where a guy's like, well, I'm flying along, and then all of a sudden it tells me I'm going south, or I'm going north, or whatever the situation is, you can always ask, like, hey, like, what were you doing whenever you noticed this? And if they're like, oh, well, like we got an altitude change, and so I put the power in, and we were climbing up. And then also it's like, okay, well, you're accelerating, or you're going down, you're accelerating there. That could potentially be the cause, and so that might help you with your troubleshooting later on. Okay, so a couple of different types of compasses that you should be aware of. Like one, vertical mounted compasses. So I told you that there are different grades. So the compasses that you'll see here in the hangar, they're going to be the old school float mounted, up on the windshield, and they spin freely. They're the simplest, and they are the most reliable in terms of it doesn't require any electricity or anything else like that to it. However, it is the most susceptible to compass errors, so it takes the most skill to kind of translate effectively. There's another one called a vertical magnet compass. By mounting the main indicating magnet of the compass on a shaft rather than a float, so it's instead of being like on a float that's floating this way, it's on a shaft that it can spin around like a wheel. Through a series of gears, the compass card can be made to turn about a horizontal axis. That actually curtails a lot of these types of errors, because instead of like spinning around or whatever else, it's geared so that way it wants to spin vertically like so. that allows, because the gearing allows you to dampen certain effects and then tighten up other areas, so that way you don't have to worry about so much drama with it. The downside is that like it can also look a lot like other instruments, and so like my plane has one of these, and I'm constantly having to like adjust it and say like, hey, look, this is where north is their machine. So it's not perfect, but it does help, especially if you're kind of a novice pilot and you're not used to all these like compass errors. Then that will be helpful for that. So a remote indicating compass, a better solution to deviation is to remotely locate the magnetic compass in a wingtip or vertical stabilizer where there is a little interference with the Earth's magnetic field. The downside of that is that like while it does solve one problem, it can create another. You're going to end up having wires that have to run up to your indicator up there. Anytime they have a lot of wires, you've increased complexity, you've increased the chance for problems with the wire, just things getting cut or whatever, or shielding could be a problem, corrosion's a problem. So it's not necessarily a perfect answer either, but it is a better one if you don't want to have to deal with all the magnetic deviation stuff. You just need to verify the compass on a regular basis to make sure that there's no problem with it. The other one, a remote indicated slave gyro compass. We're not going to talk about this one too much because we're going to get into gyros here in later classes, but this one's an elaborate, very accurate method of direction indication and has been developed that combines the use of a gyro, a magnetic compass, and a remote indicating system called a slave gyro compass or flux gate compass system. Essentially, what you're going to do is you'll get a fix early on, and then you'll program your inertial navigation system, which this is usually a part of, and it'll tell you, hey, look, like we were going north, and now we're going to turn, and we're going to do all this INS wizardry, and then it'll give us a position and tell us like which direction we should be facing. Okay, so solid state magnometers. Now this one is something that you will see more and more often, especially in corporate. You'll see a lot of these located in like the wings of general aviation aircraft that are kind of a higher caliber, nothing old, like we barely have any money and we're just kind of like trying to make it go on, but rather the fancier, nicer, newer aircraft. The solid state magnometer are used on many modern aircraft. They have no moving parts and are extremely accurate. Tiny layered structures react to magnetism on a molecular level, resulting in variation in electron activity. These low power consuming devices can sense not only the direction of the Earth's magnetic poles, but also the angle of flux of the field. They are free from oscillation that plagues a standard magnetic compass. And so like you'll see those more and more often, and a lot of times you'll end up seeing like decals that'll say like magnometer, that's right there. So that way that that's what's going on up in that wing. Those are by far probably the choice compass system that's in operation today. They're still fairly new, and they still are more expensive than what most general aviation folks want to pay. So you won't see them on smaller airplanes, but once you kind of get into the airplanes that are like north of like $500,000, they're pretty standard. You'll see them on a regular basis. So that is the characteristics and operation and the deviation problems that come with compass. Now let's talk about compass swings. Okay, so compass swing. So the first step of any compass inspection is going to be just simply looking at the compass inside of the aircraft and make sure that it's it's okay to be used. There's not like some very obvious very obvious problems with it. So here's like 4 or 5 steps from the 8083. It says the compass indicator should be checked for correct readings on various cardinal headings and recompensated if necessary. That's the compass swing. We're going to talk about that here in just a second. All right, number 2 is moving parts of the compass should work easily. Now you would think that the compass doesn't have a lot of moving parts, but it actually does. It has like little set magnets in the bottom of it that we're going to talk about here in just a second. But it also, you should be able to rock the airplane and watch the dial spin. If it hangs up or gets all like kind of cattywampus or something like that, then you probably need a new compass. They're not really that expensive. They're pretty simple devices. So don't just like deal with something, fix something. Okay. The compass bowl should be correctly suspended, and the anti-vibration device should not touch any part of the metal container. So essentially, like it shouldn't be like getting hung up or anything else like that. The compass bowl should be filled with liquid. So if you see a bunch of air in there, that's not right. That needs to get replaced. All right. So the scale should also be readable and well lit. So it means that like sometimes these compasses will get old and they start getting kind of like ratty, and you won't be able to read the small little tick marks on there. So you need to replace it at that point. Now let's say if it's in good physical condition and you're ready to go swing the compass, what does that look like? Well, the first thing that we're going to have to do is we're going to have to find a compass rose. Now, compass roses, generally speaking, are at most airports. We don't have one here. They're kind of 50-50. There's volunteer groups that go out and get surveys done at airports and then have the compass rose painted. So we're supposed to be getting one on the south ramp. We were supposed to get one last November, but it rained a lot. And it continued to rain a lot, so that messed things up. But expect if you're in the first couple classes, you could be out there helping paint the compass rose. So that way, you can learn that, but also kind of add value to the to the whole airport. All right. So compass calibration is performed when the new electronic component is added to the flight deck, such as a new radio. So that's going to be part of the thing. Like you install a new radio, you have to do a new compass swing. A complete list of conditions required requiring a compass swing and procedure can be found in AC 4313-1, Chapter 12, Section 3, Paragraph 1237. So there's like a very specific list of things that will demand us to do a compass swing. But generally speaking, if you replace anything electronic on the airplane, you got to swing the compass, because that even if it's the same model and you're doing a one-for-one swap, there could be slight variations there that throw the compass off one way or the other. And so we need to adjust that if we can. If not, at least let it be a known condition for the pilot. Okay. So once you've done this, you know that you're in an airport with a compass rose, or you relocated the airplane to a place with a compass rose. What are you going to do? So you're going to taxi over to the compass rose, and you're going to make sure the plane is in the right condition. So what is the right condition? The aircraft should be in level flight attitude for the compass swing procedure. So it needs to be level. So the main thing is with like tail draggers, they can't be sitting like this, like on the ground. You have to jack the tail up so that way it's nice and level. Reason being is that the compass is built to be in straight level flight. If it's set up like this, it's going to like look all weird, and you're not really going to be able to get a good reading. Tail draggers need to have the F end. Okay, we should talk about that. The aircraft interior and baggage compartment should be free from miscellaneous items that might interfere with the compass. So in other words, don't put your boom box back there playing music as you're doing this, because it'll throw it off. Anything that's magnetic, anything that's got, like, if you have golf clubs back there that could potentially like throw the magnet the compass off, the magnet in the compass off, take those out. And the kind of good rule of thumb is just don't have anything in there, and you don't have to worry about it. Okay, all normal equipment should be on board and turned on to simulate a flight condition. So essentially, if you're going to be flying with it, then you need to have that system on. The reason being is that the whole point of this is to make sure that we recalibrate the compass for flight conditions, so that way we understand what's going to happen if we take off and we're flying along and we're in straight level flight and we don't have anything weird in the plane that's going to throw the compass off. What is the GPS going to do to the compass, or what is the radio going to do to the compass, or the VOR, or whatever? And so we want to have all those systems on and running, so that way we can observe it on the ground before we get lost out in the middle of nowhere and end up having to do a precautionary landing because, like, we flew a compass heading that was wrong. Okay, so the basic idea of swinging a compass is to note the deviation along the north-south radial and the east-west radial, then adjusting the compensating magnets, those are all the little magnets on the bottom of the compass, to eliminate such as much deviation as possible by centering or zero the compensating magnets with non-ferrous screwdriver. Align the longitudinal axis of the aircraft with the north-south facing radial and adjust the north-south compensating screw so the indication is zero. So essentially, what you're doing is you're going to get in the plane, you're going to put it on the north-south line, you're going to look north, you're going to look up the compass, and you're going to say it should say 0. But if it doesn't say 0, if it says like 5, You're gonna take a little bitty screwdriver, a little jeweler screw, and you're gonna turn it until eventually that 0 lines up with the indicating mark. So that way you know that now the compass is calibrated on a north-south line. Now, if it's over 10% and you can't get it, you bottom out that compensating magnet, and you can't do it, well, it's bad compass. It's time to get rid of it, and we need to get something new in. Once you do that, you're going to do the same thing for the east-west. Now, at that point, you're going to do it on every single 30-degree mark, and you're going to note where where the compass reads. So in theory, you've zeroized it north-south, you've zeroized it east-west, and then you're going to do these little increments. Now, as you do the increments, you're going to turn around and you're going to say, hey, look, at 30 degrees, it's off by a degree. Well, there's a compass correction card that's tied to it, that's right underneath it. You're going to take it out and you're going to put 1 degree or whatever, or it'll say like for steering 030, steer 031, or whatever, however that compass card is set up. You're going to do that for every 30-degree radial that you go around, and then that should basically tell the pilot, hey, look, like we've got you as close to right as possible, but there's still going to be some drama to it. So like here is the list of corrections that you need to make, and it's been properly given to you in the cockpit, so that way it's not, if you get lost, it's not on us. It's because you don't know how to steer or how to navigate. Yeah, so that is how you swing a compass. It's not really that difficult to do. It's more fun, I think, because it's not really that demanding, and you get to go and taxi around and play with the airplane. And you'll see helicopters. It's interesting to watch. Whenever we used to do it in the Army, the helicopter would be out there, flying around and just hovering and swinging around. They would do all these up and downs and all kinds of fun stuff to try to throw the compass off and then recalibrate it as you need to. So compass swings, super cool little task, not really that difficult. So you should look forward to doing them.